All right, so we've been working inside of hyperbolic geometry. We've been talking about, when we left last time, we were talking about different kinds of triangles inside of the Klein model. And we had set up this Klein model, but we never really checked to see that it's really a model for our geometry. So that's actually what your assignment is going to be for, I guess you could say, this weekend. So your homework in the midst of what we're going on right now, and I'll write it out in more detail, but the basic idea for your homework is that you're going to check the incidence axioms. So that was I1, I2, and I3 for the Klein model. Now, as a way to sort of help with a little bit of that, I want to give you a few pieces of information. So just start with a note. The Klein model, it does satisfy, or we would be talking about it. The Klein model satisfies all axioms of neutral geometry. To prove this or to show this, you can translate into Euclidean terms and prove the statements in Euclidean geometry. Now the incidence axioms I1, I2, I3 are all on page 69 of your textbook. But what I'm going to do with you right now is I would like to help you with the rewriting of what the incidence axioms would look like within our Klein model. So you can reference back to page 69. It's not going to hurt anything. But 69 is a more generalized statement of what we're going to specifically write down now for our Klein model, okay? So the first incidence axiom, IA1, would say something like this in the Klein model. Given any two distinct points, A and B, in the interior of the circle, and we had a circle gamma last time, there exists a unique open chord L of gamma such that A and B lie on L. So what I would have you do, would like for you to do, is to prove all three of these incidence axioms. This is the first one, but you get this one for free because your book already proves it. So I'd still like for you to write it down, not word for word, but change it into words that actually sound more natural to you, because that's how it is anytime we write something down. If we write it in our own words a little bit, some of the words, of course, match, but it will make sense to us later. But that way you have all of this on sort of the same document, all three of the incidence axioms proved. Does that make sense? So the proof for this is actually on page 300. See, I'm even telling you where to find it in your book. It's amazing. I just did a third of your homework for you. Do you know what? There's another homework assignment as we keep going today, so maybe I didn't. All right, so this is the first incidence axiom. This one's already proven for you, but go ahead and rewrite it in your own terms for IA1. So let's look at IA2. IA2 would say something like this. For every open chord of gamma, there exist at least 2 points interior to gamma on that chord. And so you're really gonna have to prove that one. That one's not a freebie. And then IA3 is the third one. And it would say the following. There exist three distinct points in the interior of gamma such that no chord of gamma contains all three of them. So that's your homework that we'll be doing next time, is to really truly to prove these last two, to write a condensed version or a in your own words kind of version of the first one. And as you're doing that, please go back to the same note. I know a couple of you were walking in as I was writing that one down, is that to show this, to prove this, translating into Euclidean geometry and proving it in Euclidean geometry is going to be the way to go. All right, so think about what this looks like in Euclidean geometry, because the interior points to our circle gamma are the same points that Euclidean geometry would have involved, right? That's how we created it. All right, so I made this comment last time. We didn't write it down, but we will this time. Lengths and angles and things are really not the same inside of the Klein model. So let me kind of write down the reason why, instead of just having said it like last time. We would like to be able to measure angles and lengths. But Euclidean methods of measuring can't be used. For example, if we use Euclidean length, then every line would have finite length. Which would invalidate axioms B2 and C1. Which ensure all lines are infinitely long. So that's obviously a problem within this model. Everything has its limitations, and this would be a limitation of this particular model not being quite as similar as we expected to Euclidean geometry. We're going to talk about a couple other things inside the Klein model before we sort of take a step back and move into a different model, which we will get to today, I believe. We're going to talk about perpendicularity. So perpendicularity in the Klein model. And we'll start with the definition of what of something that came up actually on your GeoGebra assignment. A few of you came and talked to me about this particular problem. So if L is not a diameter of gamma, then the tangent lines to gamma at the ends of the chord L must meet at a point exterior to gamma. Do you remember what this point is called? That's right. Good job. Called the pole of L. And we're going to denote it P of L. That's some of your notation for it. And just as a reminder from that assignment that you did, here's our circle. Oops, actually, I just want it done the way I just did it. Here's your circle, gamma. And as long as we have a chord that is not a diameter, so I'll go with this one, which I will then probably have to move, we can create tangent lines to the ends of each of those endpoints on the circle. Hang on, I'm going to create it and then move it. Looks pretty good. No, it doesn't. No, I had it right the first time. Here we go. All right, I think that's fairly convincing. All right, so those are our tangent lines. Obviously, they're not drawn perfectly, but they give you the right idea. And then we've got chord L, and then this point right here would be the pole of L, P of L. And you guys created a tool. Hannah and I talked about that last class period. Created a tool that created that. So using that definition, we're going to move forward with a little bit more of what we can do with this perpendicularity business. Two lines, L and M, in the Klein model are said to be perpendicular if either of these cases hold. Case 1. At least one of L or M is a diameter okay, so if we have a diameter, then L is perpendicular to M, and that is equivalent to Euclidean. Case 2 is that neither L or M is a diameter. Of gamma. So then L perpendicular to M if and only if the extended line and we'll call it M hat passes through squeeze it in there, P of L. Actually, let me see if I can get a diagram from the other slide. Okay, so that same diagram we had before, this would be L, and if we actually had another line that's going to be perpendicular to M or to L, it would have to be passing through the pole. So this would be an example of a line M that we would consider to be perpendicular because it's passing through the P of L, pole of L, the pole for chord L. And this would be M hat. So M is the line inside, M hat is our extended line in Euclidean geometry. Note, in order for perpendicularity to be symmetric, right? We want to say that M is perpendicular to L and L is perpendicular to N. We want that to be a symmetric description. L hat must pass through P of M as well. Okay, right, so if and I didn't actually draw this, so we'll see how good I can do on the iPad doing so. But if I had a tangent line here and a tangent line here, and they're not going to work because I don't have my diagram drawn right, but the extended line L would cross through the pole created by those two red tangent lines as well, if I could draw it on one screen. So, an observation. Divergently parallel lines must have a common perpendicular. So we had two cases about perpendicular, so I'll draw both of them to give you some kind of a perspective of what this observation's explaining. So we'll actually start with case number 2, the case where we don't have we don't have a chord, we're not working with a chord that's diameter. So if I take the two chords that I would have, we'll go with this one and we'll go with this one. These would be considered divergently parallel from what we did last time. And we were to create the tangent lines. We'll see how well I've done on the screen to do so. Okay, so those are the two parallel, or the two tangent lines to the bottom chord. Use blue. And those are the two tangent lines to the top one. Told you no promises on this actually looking right in the end, right? I did make that disclaimer, just checking. Okay. So we actually are supposed to be able to, if I drew it right, which I obviously just totally screwed up. Let me see if I can make it believable. Maybe I should do it that way. So you can see if I drew it right what it would happen. I'm attempting to make it better. It's probably not going to work. All right, so if I'm going to go through that point as the pole to find a perpendicular, I'll do that point first to see if I can make the other one work reasonably well. Not so reasonably, but that would be a perpendicular right here. The observation, if I had drawn this well, and if I could draw perpendicular, or if I could draw actual, tangent lines in the screen that would work, is that this particular point, okay, so just pretend with me for a minute that it works. This yellow line should actually be going through that corner up there. I told you it's not working. I can't draw very well on this screen. Your papers can probably draw a little bit better than I can on my screen right now. But these actually should meet right here, right? That's where it should be meeting, is that particular point with my yellow line.
So these both going to be at 90 degrees?
Yep, those are going to both be 90-degree angles. Exactly. Now, remember, angles aren't measured the same way. So, Matt, you may be looking at that and going, that doesn't look like 90 degrees to me. But remember, we don't measure the same way inside of the Klein model. We haven't really discussed how it's measured. We just know it's not Euclidean measurement. So don't go get a protractor out, okay? That's case 2. Let's see if I can do any better job on case 1. All right, so on case 1, if we have a diameter as one of our chords, that looks pretty good for a diameter. And we have another one of our chords. We would actually only have tangent lines for the top one, right? Approximately something like this. And the perpendicular that comes through here would actually also create the perpendicular here, whoops, here and here. We would get perpendiculars. Now we have to, right? I mean, like, the whole idea is that these are supposed to be parallel lines, right? And so we've got these common perpendiculars showing up.
What if they're both diameters?
Then they already intersect. So that wasn't one of our cases as a possibility when we were talking about being perpendicular. Yeah. All right. We're going to give name to a couple other points that are occurring that we haven't done so yet on this Klein model. This is a multi-part definition. Points in the interior of gamma are called ordinary points. And for the most part, that's what we've been discussing, is the points in the interior of gamma. Our second type of points are points on gamma. Points on gamma itself are called ideal points. Are there any other points we could talk about? The exterior ones, you got it. Points outside of gamma are called ultra-ideal. Now I feel like I'm talking about superheroes or something. Ultra-ideal points. And one last part of our definition, this one's lengthy, is for every diameter of gamma, we're going to add in a point, add the point at infinity, oops, I don't have space there. Such that all the Euclidean lines parallel in the Euclidean sense to this diameter. Meet at this point at infinity. This is in the projective completion. Of the Euclidean plane. And we will call these points ultra ideal as well. So we're going to talk about a few facts that come as a result of having all of these different points and the lines that they create. The following will determine a unique line. First one is obviously two ordinary points. That's the one we've been working with. The second one would be two ideal points. Also what we've been working with. If we have 2 points along the outside of the circle, we can connect them with a line. All right, now one ordinary point and one ideal point. And then the last one, which we have now that we didn't have before we discussed this, is one ordinary point and one ultra ideal point. These are the ones that we're guaranteed to get a line from. And let me show you what I mean by that. So let me make the disclaimer first. The remaining pairings sometimes determine a line. So as an example to that, I'll show you just one of those such pairings. For instance, if you had one ideal point and one ultra ideal point. So a couple of things that could happen. One of the ideal points, let's say, could be here, and the ultra ideal point could be over here, and then they form a line, right? Remember, line still has to be inside of the circle. However, it could be wow, that wasn't what I meant to click on. Here's my Klein model. I could have the point here as my ideal point and my ultra ideal point here, and they do not form a line. In a Euclidean sense, yes, but not inside the circle, which is where our lines exist in the Klein model. Do you see the difference? So it's not a guarantee that they won't, but there's no guarantee that they will either. All right, so this is homework assignment number 2 that I'm about to give you before we change the model we're looking at. So this is also due on Tuesday next week. So there's 2 things you're going to do. Well, the first thing is going to be, I'm going to write down what you're going to do, and the second one is a few of the problems from the book. So you're going to write interpretations I helped you. I wrote interpretations for the incidence axioms, right? You're going to write interpretations of the rest of the incidence descriptions, like what is point, what is line, what is between, those kinds of things. So, hang on, where am I? Write interpretations of incidence and betweenness axioms for the Klein model. And understand your Klein model now has more points than what we were actually talking about before, right? And then the second thing is that you're going to look at page 348. And there's going to be a few problems on there that you're going to do. It's numbers K2, K3, parts A and B only, and K5. I think it's 424. Is it 424? Yes, nodding, good. Okay. All right, we're going to change models. Okay, so we've got a pretty good feel for the Klein model now. And we're going to take a look at a model where we still have this circle and we're trapped inside of this circle, but our lines don't quite look the same. So we're going to take a look at the Poincaré model. So we're going to fix the circle gamma. And points are going to be the interior points of gamma. Lines, or we'll sometimes call them P-lines, are a little less direct on how we write them. So there are 2 cases. One is open diameters of gamma. So we already had that as a line in the Klein model. So the second one is open arcs of circles orthogonal to gamma. So So if we have one of these open arcs, I'm going to call it delta. That's right, isn't it, Noah? That one's delta?
Yeah.
Yep, okay. That lowercase, uppercase thing throws me. I don't know what my problem is today. Most days, actually. So delta is perpendicular to gamma actually means at each point of intersection, of delta and gamma, the radii of delta and gamma through that point are perpendicular. Also, the tangents at that point are perpendicular. I promise a picture is coming soon. But before we get there, let's finish these out. The next one is betweenness. So between lies on and parallel are as usual. And the last one is congruence. Let me see if I can just shift this up a little bit so I have two lines. No problem. Congruence of angles is the usual Euclidean congruence. Using tangents, rays of arcs. So we say this model is conformal. Let me do the picture next, and then I'll make a couple of notes. All right, so here's our circle gamma. Obviously, we can have a diameter. Okay, that's a line. That's not the one you had a hard time picturing, though. This is the other kind of line. It's portions of a circle, not just any arc, but the arc of some circle that specifically hits the ideal points, what we would have called the ideal points in the Klein model, at right angles. In particular, Let me draw a couple more up here. That's not too bad. The arcs don't have to be the same length, just like chords wouldn't have had to been the same length in the Klein model, like the Euclidean visual part of it. And as you're looking at these, we still have all these right angles here. So a couple of notes about this. Angle measure was cool. We were good with that. Like it's like Euclidean. But congruence of segments, again, is complicated. With a different way of measuring, length, than the usual Euclidean way. A second note. Is that the hyperbolic axiom is satisfied by this model. And the diagram that I already drew actually confirms that. So if this, for example, is line L, or you could take the pink one as well to be line L, and this right here is point P, all of those arcs, i.e. lines at the top, would be parallel to L, correct? Through point P. Some images of what things sort of look like. Some of the things we've been talking about, what they look like in the Poincare model. I have space for a couple of them on this picture. So we'll do common perpendiculars first. So if I had oops. We'll use that one. A diameter here and a diameter here that they were perpendicular. And I have a line at the bottom. Use that one, I guess. That forms those 90-degree angles. There will be a common perpendicular there as well. Okay, so it's the vertical line, the one I've drawn vertically, is perpendicular to both pieces. They admit a common perpendicular. I drew what happened if there's a diameter, but let's actually draw what happens if there's not. I mean, if it's the other image. So I'll do it in an order that makes better sense this time. If I have this chord at the top, not chord, line at the top, and I have this line, say over here, there will be a, do it in pink, there will be a line that goes like this. That was terrible. Let me try it one more time. It's a little bit better. where I end up with, of course, it's got to be a line, so it's got to have those 90-degree angles hitting the circle itself, but they also hit each of my other two lines at a common value. Not every line will do that, of course, but there will be one that does. There will be one common perpendicular between the two at each specific point there like that. One of the ones we talked about last time was what limiting parallel rays. We did that visual last time for our Klein model. So limiting parallel rays. We can use diameter if you want. We can use the non-diameters if you want as well. So there's a diameter. If I use the diameter, I've got this sort of image going on, not drawn great, but they can meet at that point. Excuse me, that's the edge of the diameter on the ideal points or on the circle itself. Same thing over here. We could actually have two of these arcs themselves meeting along the side of the circle at one of the ideal points. They can also meet inside of the circle. So let me draw you one of those pictures. So let's say we have this arc here, and it meets with that one right there. And these actually cross. So that's a fun picture, right? They're still forming these 90-degree angles if I were drawing them well, of course. By definition, they have to be doing that. So our limiting parallel rays could look like this. And we're going to draw one more picture today of something we've seen before. These are quadrilaterals. So I'll start with a diameter on this one. We have two options. One is that we actually have two diameters intersecting. So I'll draw that picture. I could draw them on the same picture, but I'll draw them separately. And then we have an arc over here. So there's a perpendicular angle right here. And we have another arc at the top. So every time that two lines are crossing, we've got perpendicular lines, right? Except right here, there's a problem with this in that description. Oops. This angle right here, I'll point to it in green, has to be acute. Why? No rectangles. Very good, Shayna. There are no rectangles. What is this shape called when I have three right angles? Do you remember which one this one was? I think Lambert's the one with three right angles. Is it? Yeah? Okay. It's all right. You had a 50-50 shot. Way to go for guessing. This one's a Lambert one. Right? The arcs themselves don't actually have to cross at 90-degree angles, but the arc and the diameters do. So that's what you're seeing happening there. So that's why there's three of them that are 90-degree angles and one of them that's not. We also could have, wow, that was not a circle at all. Let me use a diameter again, and I'm going to create some other arcs on this one, because you guys brought up Sakari quadrilaterals, of course. All right, so like we said, these are 90-degree angles here, right? I'll look along the corners, they are too. Kind of irrelevant for my particular argument at the moment, but they are. So I have two 90-degree angles inside of this quadrilateral. We know that these summit angles would be congruent up here, and we know that they have to be acute, right? Can't be both 90, they can't be both obtuse, so they both have to be acute. And this picture would then be the secary quadrilateral. Any questions? All right, so for next time, there's 2 homework assignments to do. We finished a little bit more quickly than I expected to today. That's all right. And we will pick up next time with talking about how to create what's called an isomorphism between the Klein model and the Poincare model. If they're both models for the same type of geometry, there has to be some sort of a correspondence between them because they got to be the same in some senses for them to both actually work for hyperbolic geometry.